of 6 mini labs when I was gone in order to try to make some connections with particle theory and transfer of heat that we haven't talked about for quite a long time. This is something that we originally did in Science 7. So that was 4 years ago. And every once in a while we've touched on particle theory again. So for example, when we talked about density in Science 8 or atomic structure in Science 9. But we really haven't applied these principles in a long time. I went through the half-page sheets that you did for your pre-assessment. A couple things came up. The process of conduction was something that people felt that they could explain fairly well. There were a few people that ranked themselves low. Many people ranked themselves at a level 2 for conduction and radiation. A lot of people gave themselves a pretty low ranking for applications of heat transfer. So what I thought we'd do today is do a bit of review of particle theory and these heat transfer processes, because this next unit in physical science is all about heat and temperature. So we need to know those things pretty well in order to actually do the physical science 20 stuff. We're not simply just reviewing the Science 7 content in Physical Science 20 and calling that a unit. We're going to be getting a lot more specific with heat transfer and actually calculating the amount of heat that's transferred from one object to another. So for example, if I was to combine this amount of water with this amount of water at two very different temperatures, by the end of this unit you'll be able to tell me what the final temperature of the two together will be. It all starts with the particle theory of matter, which literally states that everything is made up of particles. Everything is made up of particles. So when we talk about the mass of a substance, we are referring to the amount of particles that is making up the substance. The sun is more massive than the Earth by a number of times. I think it's 62 times or something like that. That's because it has way more stuff, way more particles than what the Earth is made up of. Oftentimes, people confuse mass with weight. What is the difference? Why do you have a weight on planet Earth? Yes. Okay, I think somebody else said it first. Okay. It is because of gravity, which means if the force of gravity changes, so does your weight. If you go up to the moon, your gravity will be, the gravity is far less, therefore you weigh less. You've probably seen some of the science fiction movies where somebody's walking on the moon and they're kind of doing this really exaggerated bouncy step thing because they have a lack of or less gravity than here. Or if you go to Jupiter and you were actually able to stand on the surface of Jupiter, exactly, it's actually a Jovian planet, it's a gas planet, you would be far heavier. Jupiter's enormous, has more particles, more gravitational force. You would weigh more. Your mass doesn't change. What makes up you is the same whether you're here on Earth, the moon, or somewhere in Jupiter. Can't really say on Jupiter, right? There is a theoretical temperature at which particles cease to move. Do you know what this temperature is?
Kelvin or...
Ooh, what's the word Kelvin mean?
Ask Brady.
Is it minus 273 Celsius?
Okay, so Kelvin is based on this theoretical temperature. When we say 0 degrees Celsius, how did we decide what 0 degrees Celsius was going to be? Exactly. Kelvin, 0, and degrees 0 is not the same thing. 0 Kelvin is when particles cease to move. And that's minus 273.15 degrees Celsius. You'll know that by the end of next week, because you're going to have to be able to convert from degrees Celsius to Kelvin and back again.
We don't have to use Fahrenheit, right?
Pardon me?
We're not going to use Fahrenheit, right?
Not in this course, but if you were to take up an engineering job in the United States, you would likely have to learn Fahrenheit to degrees Celsius, because that's how the Americans measure temperature, but most of the science mathematical equations use Kelvin. Yeah. The nice thing is that if you go up by 1 degree Celsius, you go up by 1 degree Kelvin. If you go up by 10 degrees Celsius, you go up by 10 degree Kelvin. So 1 degree Celsius and 1 degree Kelvin is the same temperature. Temperature change, sorry. Stop too early, forgot the last word. So let's just do a quick diagram here. Let's say we have 0 degrees Celsius, which is going to be 273.15 Kelvin. If I measure the temperature and it's 10 degrees Celsius, this has increased by 10 degrees Celsius. The Kelvin temperature would also increase by 10 degrees Celsius, and it would be 283.15 Kelvin. If you were to go to Scotland, you would have to learn the 4th temperature scale. Yeah, it's called Rankine. So again, if you go into engineering and you start working with things like broilers or thermocouples, you might actually have to know all 4 temperature scales. Rankine matches with the Fahrenheit scale, but uses absolute 0. Kelvin matches the degrees Celsius in terms of temperature change, but the zeros are different. So if you look at the similarities rather than the differences, sometimes it makes it easier to understand. The movement of particles varies. As long as it's above minus 273.15 degrees Celsius, that particle's moving. It might not move very much. It depends on its state, but it also depends on its temperature. What do you remember about particles in a solid state? Are particles close together or are particles farther apart? They're packed, they're very close together. Do they have the ability to jump out of their container and move around? No, thankfully. It'd be really scary if you woke up the next morning and the salt from your salt shaker was doing some kind of like line dance on the kitchen table. We have 3 phases of matter that we talk about in high school science. Are there only 3 phases of matter? There is a missing phase, which is called plasma. Usually when we start talking about the plasma state, we're talking about things that are very, very hot. We don't have the ability to make something that hot using equipment in this lab. So we don't usually talk about the plasma state. However, that could be a possible direction for a student-directed study if you're interested in that. So we have solids, liquids, and gases. They differ in how close they are to each other, how they move, and their volume. I'll give you a few minutes with this slide. Let's look at solids first. In solids, the individual particles are very close together. They are touching each other generally. They're very slow moving. What is their movement like?
Vibrating?
Yes, they're only vibrating. Okay, so they actually don't move from their position unless you pour something or smack it and send something flying. They're sitting there and they're vibrating. You can make them vibrate faster or slower, but that's all they can do. What does it mean if they have a definite volume?
It's that volume and always will be that volume.
Pardon me?
It has one volume and will always be that volume.
Okay, and it's very easy to measure that volume, right? It might not be practical to measure the volume of a salt crystal, but you could theoretically do length, width, height of a salt crystal. They will occupy and maintain the whatever volume they're cast in when they become a solid. And this is based on how particles are attracted or not attracted to each other. That's why we see that the shape of a salt crystal is the way it is. It has to do with the sodium ion attracted to the chloride ions, and they line up because of these attractions in a cube-like shape. They vibrate around a fixed point. That fixed point means they're not moving from that place unless gravity moves them or we force them to move. Liquids also have a definite volume. I can pour a liquid into a container and measure the volume of it because that liquid takes on the shape of whatever container I poured it into. EK, what does that mean? Kinetic energy. That's a term we haven't talked about in a long time. What does it mean to have kinetic energy? Probably shouldn't be doing this because this morning I actually managed to pour my coffee grounds into the blender rather than putting it into the French press. So, if I am standing up on this, I have potential energy. Because if I step off of this, I'm going to fall. Thank you for your faith. Once I step off of this and start moving, I have kinetic energy. Kinetic means something is moving me. So, kinetic energy is energy due to motion. For example, why do you hear that knocking? Sound has to move from here, where I'm doing the knocking, to your ear. So it's classified as kinetic energy. If I take an elastic band thought I hid one in here. If I take an elastic band and stretch it out, that's potential. If I release it and it flies, it's now moving. That's kinetic energy. If I feel these containers, they have different amounts of kinetic energy. The particles in this one are moving faster. So it feels hot. The particles in this one are moving slower, and that's why it feels cold. So heat is a form of kinetic energy. Kinetic energy is a pretty broad category. So liquids have enough kinetic energy to stretch forces of attraction. Okay, what's forces of attraction? Oh, particles can be attracted to each other based on full or partial charge. If I try to take those atoms and pull them apart in this salt crystal, it wouldn't let me do it because the particles are so close together and they're moving so slow. But in liquids, forces of attraction can actually expand and pull the particles apart, or those particles might come closer together. It all depends on their temperature. The faster those particles are moving, the more those forces of attraction can be stretched. Whereas if the particles are moving slower, there's not going to be as much stretching going on. Collisions are strong enough to force particles apart. It's because of how the particles are moving. Liquids have vibrational motion in their particles, so they're vibrating. But they also have rotational motion, so they're shaking and they're going around at the same time. And because they're going around, they start to bump into each other. Now, if I start to go really fast, I'm going to bump into other things more. And those collisions can force particles farther apart. Have you ever filled up an antifreeze tank in your car? Okay, there is a level to which you fill up that tank and you don't go beyond that level. Exactly, because as that antifreeze heats up, that coolant heats up as it goes through your radiator, it's going to expand and take up more space. So if you don't leave enough room in the top of your coolant tank, you're going to have quite the little fountain after driving for a while. Gases are very interesting. They're harder to measure than solids or liquids because their particles are farther apart and they don't have definite volume. Their motion, well, they have vibrational, they're shaking, they're turning around, rotational, and they also have translational motion, which means they go in a straight line until they bounce off something. They're ricocheted, go in a straight line until they contact the next particle, ricochet after that. So they have quite a bit of energy, and the faster they're moving, the more space they're going to take up. This is why you shouldn't throw your aerosol can of hairspray into a fire pit. Oh shoot, did I just give people ideas? Okay, so in an aerosol container, you have gaseous particles. If you heat up those particles and those particles start to go faster and faster and faster, they expand in that container, and eventually that container will rupture and send shrapnel all over the place. It's not necessarily the explosion that will hurt you, it's going to be the flying pieces of metal that get embedded in the cornea of your eye that are going to cause the most damage.
That's why you wear goggles.
Particles are very random in their movement and independent because when they bump into each other, they totally break up attractive forces between them two. In the lab, capturing a gas is a little bit challenging. if we don't seal a system, the gas will generally dissipate into the atmosphere and we'll lose that. So we have to use something like this. It looks like a big long test tube.
Mr. Franklin, telephone line 3, please. Mr. Franklin, line 3.
What you do is you fill this with water completely, or some other kind of liquid. But water is generally the safest. And you fill it all the way to the top. Then, fill the sink with water. Does anybody see where this is going? Do you know what I'm going to do next? Okay, once the sink is filled with water, what I do is you put your finger over this so you don't lose any water. Oh, I got one bubble, darn. What do you think goes next? You need a way for the gas to get in. Well, you have a tube connected to your system. So if you have a stopper on your vessel with a hole, you can shove a tube into the hole. And this end of the tube goes up and into the glass measuring tube. As the chemical reaction produces gas, it goes into the tube. As the gas goes into the tube, it presses out the water. Can you see where that level of water is? This is going to be the volume of gas that I just exhaled into the tube. So as long as you can create a sealed system and only have your gas come out of one place, which is through this tube, you can actually collect and then start analyzing the gas. Some systems are fancier, and they'll have a valve up here so they can bleed off the gas into some kind of like I guess you could do a gas spectrometry and actually do the chemical composition of the gas. Neat, hey? We can do balloons if we don't have a latex allergy, and then you can measure the diameter of the balloon or the circumference of the balloon and start to do some sphere volume calculations to estimate how much gas you have produced. A student actually did this for a student-directed study. She wanted to make her own bath bombs and then do some predictions about how much stuff would be made. She actually collected and analyzed, measured the gas that was produced by the bath bombs. It's pretty interesting. As you increase or decrease temperature, particles are going to move faster and slower. So for example, if we go into the solid phase here, you see those water particles are lined up and touching each other. As we go faster, those forces of attraction are going to start breaking. The limitation with this particular visual is that it's showing translational motion in a liquid, and that's not the case. In a liquid, particles are only vibrating and turning around. They're not actually physically going up, down, so forth. What I want to show you with this animation is that as I increase temperature, those particles are going to start moving faster. Once we get into the gas phase, they're going to spread further and further apart. And if they don't have a place to escape, your container can rupture. Three transfer processes for heat. One is conduction. Most people felt that they could explain conduction really well. All right, here's a picture. Tell me how conduction works. Oh, but you said on your self-evaluation that you could explain this as a Jedi Knight of heat transfer awesomeness. You should have to squint to read the text because you already know all of this, right? All right. This is showing a Bunsen burner flame. It has a blue flame when it burns because it burns much hotter than a candle flame. A candle flame is orange because it's a cooler flame. What is going to happen to the motion of these particles right above the flame? Yes, because heat is being transferred to this. But how is heat being transferred all the way down to these particles at the end?
As the ones right above the heat are moving faster, the bump into the other ones.
So you have one particle that starts moving fast, and it bumps into the next particle, which starts moving fast, which bumps into the next particle, which starts moving faster. And that motion is transferred all the way down. Do all types of substances have the same ability to conduct heat? No, that's what you found out in that Spoke mini lab yesterday. Copper is a far better heat transfer solid than something like stainless steel. How do we manipulate that in the kitchen? Absolutely. So copper pans, oh, beautiful set of pots and pans. Very expensive. They conduct heat so well. That's why they're desirable in the kitchen. You know from working with cast iron frying pans, those take a lot longer to cook with. Make awesome stews and such, but you gotta be prepared to be spending the time waiting for that to heat up. All right, I'm going to give you a chance to write down these questions for the demonstration. I'm going to put the hot water back in the microwave while you do this. I have 3 containers of water. I have the hot water here, which I have added red food coloring to. I have room temperature water. It's been sitting for about an hour and a half to try to get to about 20 degrees Celsius. And then I have this cold water, which has had ice cubes sitting in it for a while to try to get as cold as possible. In which of these containers is the particles moving the fastest? The hot water. Okay. Where has the heat come from to make those particles move faster? Radiation in the microwave. What I'm going to do is carefully pour the hot water into the tank. Hopefully I don't drop the beaker. I'm trying to move the water as least as possible when I do this. So what you want to look for is where is that red water ending up? Yes. Alright, it's very exciting when science demonstrations work out. We have the red band of hot water up here. Why is the red hot water hanging out up here, Connor? Why does that make a difference then?
The hot water will go to the top of the surface while the cold water stays.
Why? What is going on at a particle level that allows for that separation to happen? Okay. You've already indicated that the particles are moving faster in the hot water than in the cold water. What happens to the amount of space that's taken up if something moves faster? So it becomes less dense. If we start off with room temperature water, sorry, I better write on the board because we have absent people. If we start off with room temperature water and the particles are moving slower in that space, then compare it in hotter water. Trying to make my square about the same size. Because of bumping between the particles, those particles are going to send each other farther apart. Because the particles take up more space, but the number of particles is the same, it becomes less dense. And less dense fluids float near the top. All right. Try this one. Trying to move it as slow as possible. If you ever want to replicate this demonstration for littles or to wow a science teacher, the trick is to go as slow as possible so that you don't move the particles around too much. You want to be able to let the particles sit where possible. I think I might have moved the top layer too much. Oh, it actually hurt. Oh, this is awesome. Where's my cell? Oh, this. Doesn't always work out.
Just shake it. Shake it, man. Rock it.
Awesome. So if you're coming around this area, try not to move the table because moving the table will create a wave. Where are the blue particles hanging out right now?
Bottom.
Why?
Because they're more dense.
They're moving slower, they're going to be closer together, and they're less dense. But you start seeing something happening at the boundary. So, right in between here, you're starting to see the blue come up.
Excuse me, is there a golf in there?
No, class.
Wrong class, sorry.
Why is the blue particle starting to come up?
They're getting more.
They're getting warmer.
Less dense.
This was ice water, so it was probably about 6 or 7 degrees Celsius before I put it in. The tank was about 20 degrees Celsius, and then we have the boiling hot water up top. So the cold particles are warming, and they're going to start moving up, because as particles become warmer, it's because they're gaining energy and they're starting to move faster, and they're going to take up less space. So we'll let this sit. Just take a look at it every once in a while and see what it's doing. After, let's say if we were to check this at the end of RTI, what do you predict this tank will look like? Why? The cold water is going to start to rise as it gets warmer. The hot water is going to start to fall as it becomes cooler and more dense. That rotation in the fluid is called convection. Oh, okay, let's go back here. I'll insert a slide.
In the summer. They come in the summer hard. You should do all of them. Yeah, he uses his tape like those. I'll be like, every truck.
John's already chipped
What?
Yeah, she smashed her up to nice head.
Convection happens in any fluids. Do you remember what a fluid is? We would have talked about this in grade 8. A fluid is anything that can flow, which means all liquids and gases are fluids. Convection takes place in water. Convection takes place in air. Eagles will use convection currents to help them migrate. They will look for the darker areas, fly over those, because that's where warm air is rising. They'll be pushed up, and then they'll glide, and they'll look for the next darker area, fly over that will push them up again, then they'll glide to the next area. We use the same principle for hang gliding or using the glider planes as well. You can go for quite a ways. Of the 3 heat transfer processes, the last one was the one that people expressed the most difficulties with in their pre-assessment checklist. It's radiation. We have attributed a lot of bad characteristics to the word radiation because of events like Chernobyl. Or we hear about nuclear explosions in a submarine and we get really, really worried about the radiation that's released from that. Radiation is actually a really, really big concept, and it includes many forms of energy. For example, X-rays. X-rays, yes, they can be bad for you in a high enough dose, but we use them all the time for CT scans and for X-rays to look at your bones. That's a form of radiation. This, up here in front of the room, is a radiator. How does the heat get from here to there? It could by convection, because the warm air will rise. But if you're sitting up here, standing up here teaching, you can feel the heat waves coming off from here. And it's really, really uncomfortable some days when this thing is really going. You've used this with maybe a little itty bitty room warmer. Have you seen those parabolic dishes that people will sometimes put in a shop or a basement in order to heat up their space? You have to be really, really careful with these because they get extremely hot. And if there's a flammable material next to them, it can start the room on fire. If you feel here, you can feel the heat coming off of it. Have you ever looked down a stretch of highway on a hot summer day and you see that shimmering effect? Those are heat waves coming off of the pavement. That's heat transfer. The heat is actually rising off of the pavement. Campfires will radiate heat. The closer you are to that campfire, the more intense the heat is, versus if you're farther away, less intense heat. This is what warms up our entire planet. It takes about 8 seconds for the radiation from the sun that's going to warm our planet to get from the sun to the earth. If the sun were to go out, we'd be in pretty big trouble really fast. On Monday, I'm going to give you some application questions of these 3 heat transfer processes and see if you can connect the sciencey stuff with how we actually use this in the real world.